Welcome to chapter 6 of this paper. From this chapter we are going to start a new topic called graph theory. Graph theory is an important branch of discrete mathematics. Graph theory has a lot of applications in different subjects. Now in this module, the module 1 of this chapter 6, we are going to discuss basic definitions of graphs. First we will introduce what is a graph, then we will see basic definitions like degree of a vertex, even vertex, odd vertex, degree sequence, etc. We are also going to classify the graphs. That means graphs can be classified as directed graphs, undirected graphs. Graphs also can be classified as finite graphs, infinite graphs. Another classification of graphs is simple graphs and multiple graphs. In chapter 6, basic concepts and definitions of graph theory. In this first module 1, we are going to discuss introduction to graph theory. So the objectives of this module are introduction to graph theory, different types of graphs, degree of a vertex and degree sequence. So graph theory is an important branch of discrete mathematics which has number of applications in diverse areas such as computer science, natural science, social sciences, engineering, ecological and management sciences. It is believed that graph theory had its beginning in 1736 when Euler considered a general case of Königsberg beach problem, which is stated below. If you look at the diagram, here we have 4 islands, island A, island B, C and D, and these 4 islands are connected by 7 bridges. There is a bridge 1 between island A and island B, also bridge 3 also connects between island A and B, and bridge 2 is from B and C. So like that these 7 bridges are connected. Now the problem is one has to start at any island and has to come back to the same island by crossing each edge exactly once. So this is called a Königsberg bridge problem. So we will state now. Consider the picture above. Is there a walking route starting at an island X, say, and crosses each of the 7 bridges exactly once and return back to island X? So it took 200 years before first book on graph theory was written. This was by König in 1936. Since then, graph theory has developed into an extensive popular branch of mathematics which has been applied to many problems in mathematics, computer science and other scientific and not so scientific areas. Definition of a directed graph. A directed graph, in short digraph, is an ordered pair x equal to v comma e, where v is a non-empty set called vertex set and E is a subset of v cross v called edge set. Note that we also use v of x and e of x to denote vertex set and edge set of digraph x respectively. If E is equal to u comma v belongs to E with u not equal to v, then the edge E is said to be incident from u to v, or u is said to be the initial vertex and v is the terminal vertex of E. An edge from u to u, that is same vertex to itself, is called a loop. For example, if you look at this graph, there are directed edges from 1 to 2, 1 to 3 as well as from 3 to 1, 3 to 4, 4 to 2, and there is a self loop at vertex 1, 4 to 4. That is, in the above graph x is a directed graph with vertex set as 1, 2, 3, 4 and edge set as ordered pairs. It is because it is a directed graph. So 1, 2, 1, 3, 3, 1, 3, 4, 4, 2 and 4, 4. The edge 1, 2, 1 is called initial vertex and 2 is called the terminal vertex. Similarly for other edges. There is a self loop at vertex 4. Now we define the graph. A digraph is said to be a graph if uv belongs to E whenever vu belongs to E. For any 2 elements u comma v belongs to V, that is for any 2 vertices u and v. If u comma v belongs to capital V, then edge between u and v in the graph x is denoted by unordered pair u comma v. Now it is because once uv is there, v is also there. So we will simply denote undirected edge. Just now we proved first theorem on graph theory, which says that sum of the degrees of all vertices is equal to twice the number of edges. Now we are going to define concepts like odd vertex, even vertex, pendant vertices, and so on. And also we are going to show that the number of odd vertices in a graph is always even. In this case, we say that E is incident with U and V, or the vertex U is adjacent to the vertex V, or vice versa. If two edges E1 and E2 are incident with a common vertex, then the two edges are said to be adjacent. For any finite set S, the cardinality, that is cardinal modulus of S, denote the number of elements in S. Then a graph or diagraph is said to be finite if mod V, that is the number of vertices, is also called order of the graph X, and mod E, that is called size of the graph X, are finite. That means the number of vertices are finite as well as number of edges are finite, then the graph is said to be finite. There is a possibility of having more than one edge between two given vertices of a graph. In that case, those edges are called multiple edges. If a graph contains a finite number of vertices but infinite number of edges, then the graph contains at least two vertices which have infinite number of edges between them. An example of a multiple graph, a graph which we will give below contains multiple edges between vertices 1 and 2 as well as 2 and 3. So one can see that there are two edges between 1 and 2 and two edges between 1 and 2 and 3. So this is a multiple graph. A graph is said to be simple if it has no loops and no multiple edges. Now degree of a vertex. If x equal to v comma e be a graph, then the degree of a vertex v is denoted by d of v, is the number of edges incident with it. In case v is a vertex of a diagraph X, then we define in degree and it is denoted as d plus of v. It is the number of edges incident to that vertex, as number of edges that have v as a terminal vertex. Out degree of v, it is d minus of v, is the number of edges that have v as a initial vertex, that is number of edges which are coming out of v. So now we are going to give an example of a graph. Let us take A equal to 1, 2, 3, 4 and B set of two element subsets of A. Now we construct a graph with B as vertex set and there is an edge between two vertices whenever their intersection is non-empty. For example, here we are taking two element subsets of A, that is 1, 2, 1, 3, 1, 4, 2, 3, 3, 4 and 2, 4. These are all two element subsets. Now 1, 2, 1, 3, there is a edge. It is because their intersection is non-empty. 1 is common to these two sets. There is no edge between 3, 4 and 1, 2. It is because there is no element common to these two sets 3, 4 and 1, 2. So like that we constructed the graph. This graph is denoted as J 4, 2, 1. Here 4 represents the original set A contains 1, 2, 3, 4 and we are collecting two element subsets, that's why 2, and their intersection is contains exactly one element. So that's why it is denoted as J 4 to 1. In general, we can generalize this definition as let n comma k comma I belongs to Z plus n greater than or equal to k greater than or equal to I. Let S be a fixed set of cardinality n. Then the Johnson graph denoted J n comma k comma I and is defined as follows. The vertices are k element subsets of S and two vertices are adjacent whenever their intersection has size I. So now we are going to define another graph called Peterson graph. Here we are going to take A as 1, 2, 3, 4, 5 and B is set of all two element subsets of A. Now we construct a graph with B as vertex set and there is an edge between two vertices whenever their intersection is empty. This graph is commonly known as Peterson graph. If you look at here, we are taking two element subsets from the set A and there is an edge between two vertices, that means two sets, if their intersection is empty. Now we will define another graph called k cube graph. Let k belongs to n, then k cube graph is denoted as by qk and is defined as follows. The vertex set of qk is set of all 2 power k binary k tuples. Two vertices are adjacent whenever they differ in exactly one coordinate position. For example, here we are taking binary sequences of length 1. So only 0 and 1 are two binary sequences of length 1 and they differ just exactly in 1 bit. So we have q1 and q2 binary sequences of length 2. So 0 0 0 1 1 1 and 1 0. Look at, there is no edge from 0 0 to 1 1. It is because there is a difference in two binary sequences, but 0 0 0 1 there is a difference in only one sequence. Similarly 0 1 and 1 0 also there is no edge. It is because 0 changed to 1 and 1 changed to 0. And similarly q3 is graph is defined with three binary sequences of length 3. Now we are going to define the first theorem on graph theory. It says that sum of the degrees of all vertices is equal to twice the number of edges. So we can prove the result by induction on the number of edges. If there are no edges in the graph, then the degree of each vertex is 0. Thus the result follows trivially. Assume the result is true for all graphs with k edges. Let x be a graph with k plus 1 edges and y be a graph obtained from x by removing an edge. So then y has same vertex set as x, but one edge less than the graph x. Then graph y has same vertex set as x, but contains only k edges. Thus by induction hypothesis, sum of the degrees of all vertices in y is 2 into k. Hence by adding an edge back to y, that is say u equal to u comma v, we will get the graph x. We see that degree of the incident vertices u and v, the in degree and out degree in case of directed graph, increased by 1. Hence their contribution to sum of the degrees is increases by 2. So we got the required result. For a directed graph, the above theorem can be restated as the sum of in degrees of all vertices is equal to the sum of the out degrees of all vertices, which is equal to the number of edges. Now we are going to give another example of a graph, knight graph. A knight is a chess piece that can move either two spaces horizontally or one space vertically, or one space horizontally or two spaces vertically. Consider an n-cross-n chessboard. We define a knight graph denoted knight of n as the graph with vertex set v is equal to I comma j, ordered pairs I comma j, 1 less than or equal to I less than comma j less than or equal to n as its vertex set, and edge set as I comma j and k comma l. There is an edge between I comma j and k comma l if modulus of I minus k comma modulus of j minus l is the set 1 comma 2. That is, there is a vertex for every square of the board and there is an edge between two vertices exactly when there is a knight move from one to the another. For n greater than or equal to 8, the knight graph knight of n has 4 vertices of degree 2, that is at the corners 1 1, 1 n, n 1 and n n. There are 8 vertices of degree 3, that is 1 2, 2 1, 1 n minus 1, n minus 1 1 and so on n n minus 1, and 4 into n minus 3 vertices are of degree 4 and 4 into n minus 4 vertices of degree 6. So it is better to determine all these, why we have these degree sequences. n minus 4 whole square vertices of degree 8. Try to find out these vertices as well. So the number of edges now, according to first theorem on graph theory, sum of the degrees of all vertices is equal to twice the edges. So the number of edges is equal to 4 times into 2 plus 8 times 3 plus 4 n minus 3 into 4 plus 4 into n minus 4 plus into 6 plus n minus 4 whole square into 8 by 2 gives the number of edges, which is equal to 4 times n minus 1 into n minus 2. So the number of vertices are n square, the number of edges are 4 into n minus 1 into n minus 2. So now we are going to define what is even, odd, isolated or pendant vertices. Let x equal to v comma e be a graph and v belongs to capital V, vertex at V, then if degree of v equal to 0, then V is called isolated vertex. If degree of V equal to 1, then V is called pendant vertex. Pendant vertex is adjacent to just exactly one vertex. If degree of V is even, then V is called even vertex. If degree of V is odd, then V is called an odd vertex. So this diagram illustrates, if you look at even, whenever we wrote even, so the degree is 2. For odd vertices, for example, there is one vertex of degree 3, so it is odd. Isolated vertex means that no other edge is incident with that vertex. Pendant vertex, only one edge is incident with that. So degree sequence, let x be a graph on n vertices, then the degree sequence d1, d2 and so on dn with d1 less than or equal to d2 and so on less than or equal to dn is a degree sequence of x, where d1, d2, dn are degrees of vertices of x. The degree sequence of above graph is 0, 1, 2, 2, 3. It is because there is one isolated vertex, so we have 0. There is one pendant vertex, so 1. There are 2 even vertices with degree 2 and one odd vertex of degree 3. Let x be a simple undirected finite graph, then we use the following notations. Capital delta f x is the maximum of degree of v and small delta of x is minimum degree of v. Let x be a simple undirected finite graph on n vertices, then using first theorem on graph theory we have that minimum degree is greater than or equal to 0 and that is less than or equal to degree of any vertex, which is less than or equal to maximum degree of the graph, which is less than or equal to n minus 1. The degree of a vertex maximum is n minus 1. Note that we are here assuming x is a simple undirected finite graph on n vertices, and delta of x into mod v is less than or equal to 2e, 2 times number of edges, and capital delta of x into mod v is greater than or equal to 2 times the number of edges. The number of odd vertices in a graph is always even. So the corollary, the number of odd vertices in a graph is always even. The proof goes like this. Let x equal to v comma e be a graph. Let d of v denotes degree of the vertex v belongs to v. Then from the first theorem on graph theory we have that sum of the degrees of all even vertices, that is A is all even vertices if you take, B is set of all vertices, then sum of the degrees of even vertices plus sum of degrees of odd vertices is equal to 2 times the number of edges, and sum of the degrees of odd vertices is an even number. So odd plus odd plus odd plus and so on is equal to even number. So the number of odd vertices has to be even. So this is easy to see. So now we are going to solve few problems to understand the concepts which we developed in this module. From now onwards, unless specified otherwise, all graphs which we consider are assumed to be finite graphs and simple and undirected graphs. The first problem is, let x be a graph in which there is no pair of adjacent edges. Then what can you say about degrees of the vertices in x? So the proof is easy. Since there are no adjacent edges, the degree of each vertex is either 0 or 1. Whenever if the degree of the vertex is 2 or more, then 2 edges will incident at that vertex. So, automatically we have adjacent edges. Now, the next question is there a graph with a degree sequence 1, 3, 3, 3, 5, 6, 6. Here it is easy to see that the number of vertices of odd degree, that is 1, 3, 3, 3 and 5, there are 5 vertices of odd degree. So, we cannot have a graph like that. It is because there is no graph with a degree sequence. It is a direct application of corollary that says that number of odd vertices is always even, but here we have number of odd vertices, odd number of odd vertices. So, it will not going to happen. So, now another question is there a graph with a degree sequence 1, 1, 3, 3, 3, 4, 6, 7. Here if you look at the number of odd vertices are even, but does not mean that there exists a graph with a degree sequence. So, we need to analyze carefully. In this case, the number of odd vertices is even, still there exists no graph with a degree sequence, that we will show now. To get a contradiction, let us assume that there is such a graph. One has the following observations. From the degree sequence, we see that the graph contains 8 vertices, that is the degree of one of the vertex is 7, hence there is an edge from that vertex to all other vertices. So, diagrammatically there is one vertex, there is an edge from that vertex to all other vertices. There is a vertex of degree 6 as well. So, now they will take another vertex and there is we are going to connect this vertex to all other remaining vertices, so that its degree is going to be 6. So, even without drawing the remaining edges, we see that degree of 7 vertices is at least 2, and total there are 8 vertices, but only till now one vertex is of degree 1, but in the degree sequence which is given to us, there are 2 vertices of degree 1. So, that is not going to happen. So, we cannot have a graph with degree sequence. Let x be a graph with n vertices and exactly n minus 1 edges, then prove that x has a vertex of degree either 1 or 0. On the contrary, assume that the degree of each vertex is at least 2. Then from the previous theorem we have that the cardinality of E is greater than of the degrees of all vertices is equal to twice the edges. This is a contradiction for number of edges is exactly n minus 1. Prove that in any simple graph that has more than one vertex, there must exist at least 2 vertices of the same degree. As we know that in a graph with n vertices, the degree of each vertex is the number lies between 0 to n minus 1. So, a maximum degree of a vertex is n minus 1 and minimum degree is 0. So, there is a possibility having 0 and n minus 1 also. Consequently, if no 2 vertices have same degree, then there are vertices of degree 0 as well as n minus 1. So, but a vertex having degree n minus 1 only if it is adjacent to every other vertex, hence no vertex can have degree 0. Thus, the result follows. In this module, we constructed graphs in 3 different contexts. In the first context, we taken any set and considered some proper subsets of fixed size and we constructed a graph. And the second context, we took a binary sequences of fixed length. In the third context, we took a problem from a chess problem. So, these examples suggest that the graph theory can be applied to different subjects and different areas. So, now unless specified otherwise, for us a graph means undirected graph, simple graph and a finite graph. With this, we end this module.